So what we're going to do today, we are going to get into the topic of spring design. And kind of teased you a little bit last time. Whenever you do design, it involves making decisions, right? That's kind of the essence of design, is you decide, how to specify certain things, whether that be the material that something is made out of, or whether it be dimensions, or whether it be a shape. There's a lot of different ways that you can go about specifying what a mechanical part or system, how it is going to be built or work. So we're going to do that now with respect to springs, and this problem is going to introduce a couple of new elements that we haven't really done before. First of all, we're going to talk about the strength of spring materials. Spring materials typically work a little bit differently than some of the other materials we use. They are very high strength materials, and very often they are size dependent. So depending on the diameter of the wire, we end up with a different amount of strength in the material. So that's going to be a little bit different. The other thing that we're going to do is apply a couple of kind of constraints to ourselves to try to find a good spring that will meet certain demands. And one of those includes a factor of safety against yielding the spring when it goes all the way to its solid height. All right, where I say down here, target at least a factor of 1.2 against yield at solid height. That's a common constraint to apply to springs, and it's done so that no matter what, you can kind of always expect that your spring will maintain its height, even if someone, either on purpose or accidentally, pushes the spring all the way down to where the coils touch each other. The spring will then still maintain its overall height as long as you have a factor of safety against yielding, even if you take it all the way to that length. We have a number of things that we can control for this spring. We can control the number of coils, we can control the wire diameter, and we can control, well, there's actually, that's I think the two factors we're going to try to control for this particular spring. But what's a little bit interesting is those factors are linked to other constraints that might be what we call a priori decisions. So on this particular problem, one of the a priori decisions we are making is that we are going to use music wire as the material. Okay? Sometimes there's a good reason why you might want to pick a certain type of material before you ever get started. Music wire is a really good choice for if you want a relatively inexpensive spring that, typically it's for small diameter, and so that's a common one to use. There are other types of materials out there as well. They work similarly to music wire, and so I'll just kind of mention that. We're going to ignore the spring mass for right now. We need for this spring to fit over a rod. That does a couple things for us. Last time we looked at stability against buckling. If you fit a spring over a rod, you typically no longer have to worry about buckling because it offers a constraint that holds the spring and keeps it from buckling. So we don't have to worry about that. But we do need to consider a little bit of clearance between the coils of the spring and that rod, or else there will not be the kind of motion, freedom of motion that it will need in order to slide. Okay? So these are some of the constraints that we are going to apply. We're also going to assume that the set is not removed from the material. Basically what that means is there's a kind of a second process you can do in springs sometimes, that after you have wound it, you wind it so that the free length is a little bit longer than it needs to be, and then you intentionally squish it down to the point where you intentionally yield it. And when you do that, it basically creates a different kind of residual stress in the spring wire than you would have had from it just being wound. All right? And that residual stress that you leave in the wire ends up being beneficial. It ends up making a stronger spring if you do that process where you basically wind the spring longer than it needs to be beforehand, and then do an intentional piece of the process where you push it back down and yield it on purpose. So then when it comes back out, it will be a shorter length, and it may end up being the length that you want it. And now you have induced a beneficial residual stress in the spring. Kind of what you think about that is the spring is primarily experiencing torsion, and it experiences the most torsion out on the outer surface of the spring wire. And so if you induce this residual stress, it basically causes the shearing stress in the outer surface of the wire to be going the opposite direction of what it will eventually be whenever you push the spring back down. So anyway, that kind of gets off into the weeds a little bit. For now, we just need to know that we're planning on not doing that process. Instead, we're going to just have a kind of an as-wound spring. All right, so there's a couple of initial things here. I guess the other thing I need to describe here is that we are doing a problem where there's a couple of other constraints. We're going to shoot for a 30 centimeter free length. Okay. We also want, for when there's a 50 Newton force applied to the spring, we want for there to be 100 millimeters of deflection. Okay, so these are a couple of geometric constraints. These are often ones that would be applied in a real mechanical system. Okay, so we're going to use those as some initial constraints. And not only that, we need for this weight, if it is dropped from a 1 centimeter height above the point where it makes contact with the spring, we want for there to not ever be any of the things that would constitute failure for our spring. So let me kind of describe. We don't want to exceed the yielding stress. We also don't want it to go solid whenever we release that, and it's going to actually drop to a lower height than this resting position of 100 millimeters. And we essentially need to account for that maximum amount of stress in the spring when it absorbs the weight falling. All right, so where do you want to start with this? We need to design this spring. That's a pretty open-ended thing. So where do you want to start? Okay, so someone mentions the diameter of the wire. All right, that is one of the very first things that we will do. One of the other things that I will mention here, it's written down, but we need to choose a standard wire diameter. This is kind of similar to our discussions of, we kind of talked about this, I think, a little bit with respect to bolts and stuff. You don't want to just specify any old length of bolt. You want to choose things that probably already exist, right? So that you don't have to have something special made just for you. So this is going to be another one of those examples where we're going to try to choose some standard diameter of wire and let that be another one of our constraints. This is sometimes known as a discrete design decision because there are discrete values that we can kind of snap into as opposed to having more of a continuous variability of the diameter of the wire. So that's it's a good suggestion. Before we really get there, though, we need to know a few more things about this system. Okay? One of the things that I would suggest we need to know is what kind of a spring constant is implied by what we are showing with our given information. So that we can infer from the given information that we have some kind of a spring constant. How do I determine what that is? Okay. Yeah, K is equal to F over delta. Okay, and this is just going to be equal to 50 newtons over 100 millimeters. Right, and what this ends up being is half of a newton per millimeter. Okay, so that's one of the things that's good for us to know is what is this spring constant. That's going to be important when we start getting into the process of really designing this. The other thing that I want to do is think about the condition of this spring when the 50 newtons drops and it achieves its maximum deflection that we're expecting it to have to be able to withstand in service, right? How do we do that? What's probably our best technique of dealing with that? Probably an energy method, all right? That's what comes to mind first thing here. The reason I think of an energy method is that if we're assuming the spring is massless, then we can assume that the collision that happens between these two pieces wastes a negligible amount of energy. And in that case, we can essentially think of this system as having a certain amount of energy due to potential energy at first, and then a certain amount of elastic energy stored in the spring at that maximum deflection. And we can equate those two together using an energy technique. And here's what that looks like. The equation that we use for elastic energy is 1/2 K delta squared. Okay, and we're basically saying this is the energy at the end of the process of dropping it. This should be equal to the amount of potential energy that was in the block before it was dropped. Okay, and that would be mgh, right? Or m times g is just the weight of the thing, so it's just going to be equal to 50 newtons. Okay, or maybe I'll just do it in variables first. Weight times, and then here we want to have the total height change. Okay, and so for us, what this looks like is we've got 1/2 of 0.5 newtons per millimeter. And we don't know how far the spring is going to deflect as a result of this, so that delta remains a variable, the variable we're going to solve for. We put this equal to 50 newtons times the total height change. Well, what's the total height change of the weight? Right, 1 centimeter of the initial drop, and then it touches the spring, and then it will continue to go down further until it reaches 0 velocity. And so basically what that means is that we would have 10 millimeters plus, because that's 1 centimeter, plus the amount of deflection that happens in the spring. Okay, and in the interest of time, we have a good bit to get through today. I'm going to just go ahead and tell you that if you solve this out, it ends up telling you that delta is equal to 20.95 centimeters.
Where's that equation come from? You know, like what number of page?
The equation that I used right here? Yeah. This one? Okay. That one didn't come from anywhere in particular, right? This comes from your dynamics class, where you dealt with energy methods. You dealt with, work energy. And what we did is we said the amount of elastic energy at the end final is equal to the gravitational potential energy at the beginning. Okay, and it's because all of that energy is stored as that gravitational energy beforehand, and after the process happens, when you reach maximum deflection of the spring, then all of your energy at that point is stored in elastically deforming the spring. Okay, so this just comes from work energy methods that you covered when you were in dynamics. Okay, all right, so now that we know that that's the deflection, how much force do I have in the spring at my maximum deflection? So I could even put a little subscript on here if I want, that this is my maximum deflection that I'm going to expect in service. And so my maximum force that I expect in service is just equal to 1/2 of a Newton per millimeter times a deflection of 20.95 centimeters. That would be 209.5 millimeters. This ends up giving me 104.75 newtons. Okay, so these are all some handy things that we will use in just a moment when we get ready to design this spring. There's one other one that I want to go ahead and take a little space on this page to describe, and that is if you have a spring over a rod, okay, then that means, I'll make a little sketch of that real quick. Let's say this is the rod that you're putting the spring around. And then here's the kind of a cross section of the spring. You have one of your wires right here, and we're saying that we want 0.5 millimeter of diametral clearance. Okay, and so that basically means that where this the other coil kind of comes back around, and you see coming out of the page there, right, these being the cross sections of the spring. If we have the diameter of the rod right here, then that means that the mean coil diameter, which is usually the number that we're really interested in, right, has to be equal to the diameter of the rod plus what? Okay, this little piece right here is the diametral clearance. All right. Okay, and that's usually something that experience kind of teaches you what that minimum value has to be so that you don't end up binding, the spring doesn't end up binding on the rod that it's moving on. For us, it's just given to us as 0.5 millimeter or so. So we have to add the diametral clearance. But then what else do we need to add? Okay, plus the diameter of the wire, which I'll go ahead and put wire on there. A lot of times we just use lowercase d when we're talking about wire. This is how you calculate what that mean coil diameter has to be. Okay. All right. So these are kind of the few of the initial steps that I wanted to walk us through. When you get ready to do one of these discrete design type of a situations where we're trying to, go to use one of these standard wire diameters, it is very handy to do this in a spreadsheet. All right, and so I am going to move over now and start filling out a spreadsheet that will help us with this, with this design. All right. So here is the beginnings of this spreadsheet that I would like to try to build, okay? You see there's a few things right there at the beginning where I have the diameter of the rod. I have a little diametral clearance value right there of 0.5 millimeters, okay? A few other of the parameters that were given at the beginning, I've got that the this is not static, this is the solid factor of safety. This is the factor of safety against yielding at when the spring goes solid. And something to note here is that this is a minimum value. So what that means is that if I have a factor of safety larger than that, that's okay, but I don't want a factor of safety smaller than that, at least if I can help it. Okay? All right, so the next thing I've got is that my static load is 50 newtons, and my amount of deflection that I have whenever it, drops down is going to be 100 millimeters. And then I use my spreadsheet to calculate what my K value is there. Okay, all the rest of these values are just items that we can enter if we wanted to edit what this problem, kind of how the problem worked. Okay, this value right here is another one that is just a given in the problem. All right, and then my maximum force, I suppose that's, I went ahead and just put the value in there. What would be a better thing to do right there, you think? Yeah, it'd probably be a better idea to go ahead and put the calculation in there. For what I'm doing, since I'm not planning on editing these very much, let me just leave it alone. I'll just keep it at 104.75 newtons. All right. And what you see here is I've got this table set up, and we're going to go through each of these items in this table to find them so that we can end up having numbers that give us an idea of whether or not our spring that we have designed is, is a good design, right? It gives us some guidelines on page, give me a moment, page 520. There are a few guidelines for how you know when you have gotten a spring that seems to be within certain parameters that are good. And so we'll keep those in mind, those parameters on page 520. But for right now, let's go ahead and start putting this table together. One of the first things you see here is that I have listed out a few of the gauges of wire that I think might be around the size that might be an appropriate size. If you're not sure about this, you just have to start somewhere and start putting some numbers in, and you start realizing, oh, I was way off with my first guess. I've got to put in a different number. But I've got a few of these values already put in here. Okay. If you flip way back to table A28, it's way near the very back of the book. It's a 2-page long, I believe, 2-page long table. And there are a number of different kinds of wire that are listed in that table, all right, kind of different standards of wire. There's a American or Brown and Sharp. There's Birmingham or Stubbs iron wire. United States standard. There's all these different standards of wire, and what's a little bit tricky on this is that each of these standards, they all typically use the term gauge, right? But those gauges aren't necessarily uniform between those different standards. Okay, so this ends up making it a little bit complicated. One of the tasks that you sometimes have to do is make sure that if you're considering a certain type of wire to make a spring out of, you need to make sure that you are aware of what standard is being used when you're talking about the gauge. And they actually help you with that a little bit here because it tells you kind of what the application is as principal use. So anyway, I just kind of wanted to talk through that just a little bit. We are in music wire, so that's pretty unambiguous, right? We're using a music wire. One thing that I will say on this is that if you've opened to table A28, there is a little bit different thing you see happening with music wire as opposed to the other kinds of wire, okay? For music wire, as you increase your gauge number, what do you see happening to the diameter? It increases, okay? Look at everything else in the table. All right? I think everything else, I should kind of look through that and make sure I'm not lying to you. Yeah, I believe every other standard, as the gauge increases, the actual diameter of the wire decreases, okay? So just understand that, we have this weird exception, and it's the music wire. And so that's, that happens here. It doesn't necessarily happen other places. And so I'm looking at a 28 gauge through 33, basically, for my little range that I'm going to be considering. And that happens on the second page of the table. And hopefully I didn't make any errors as I transcribed the different diameters in inches over into my sheet right here. Okay, if anyone sees any errors there, please let me know. But I think I got them transcribed correctly. Okay? Well, this is important because we're trying to limit ourselves to only using those diameters, okay, for our problem. That's interesting because it creates this discrete problem. It also kind of helps us out a little bit because we don't have an infinite variability of the diameter of the wire. All right? For various things, we might need to know this diameter in millimeters or sometimes in inches, so I have millimeters computed here for each of those values in inches. All right, so the first thing we're going to do in this table is handle the idea that the strength of this spring is no longer going to be just a constant value. What you will notice here, and it starts on page 517, there's a table 10.4. All right, And up at the very top of the table, it gives you the equation. That equation also exists on the previous page. It's equation 1014, but it repeats it again on the top of table 10.4. It says that the ultimate strength value for these spring materials can be computed with this empirical equation A over d to the m. All right, where A is a constant and m is an exponent. Okay, and so what we need to put in here are the correct values for the type of wire that we have. And so it says the material that we're using here is a music wire down in the table. And the diameter, it gives a diameter range through which these parameters are, applicable. All right, and it tells us that A is going to be 201 if we are dealing with US units. All right. Now, do you want to deal with US units or do you want to deal with SI units? Okay, probably SI units. So let's actually hop over to the one that's in the SI, and this is going to yield a value to us that is in megapascals. So this calculation ends up being 2211 divided by the diameter value, which will be in millimeters. Okay, and make sure if you're going to use this empirical equation with this data in the table, use millimeters for that length unit. All right, and then it says take that to the exponent of 0.145. Okay, and this gives us an ultimate tensile strength for this material. While I'm here, and before I kind of move away from this table, let me also draw your attention to another column that's in the table. It says relative cost of wire. Okay, it becomes a little bit useful if we begin using a value that they define on page 520 called a figure of merit. The figure of merit that they have on 520 is basically a technique of after you've designed everything else for your spring and you have more than one spring that meets your criteria. If that happens, then you have to have some way of choosing which spring that you want, and you can use the figure of merit as the very last parameter that you use. And what they suggest here for the figure of merit is basically reducing cost to its minimum. All right? And so what they give you with this relative cost value in this table is at least one way of estimating about how much do you think it's going to cost for the material involved in one spring versus another. Let me go ahead and say I don't particularly love this technique because what it does is it gets you to practice a little bit using things that aren't as real for something you'll probably have to do later for something that is more real. So in real life, you wouldn't look at this information from this table for the relative cost of the wire. What would you do? You'd probably have some idea for the actual vendor that's going to be selling you the stuff, what it's going to really cost. Okay, so anyway, but I figured I'd mention that because there is a technique after you've done all the rest of your design, and if you have more than one thing that works, there's a technique of picking which one, and it involves reducing the cost to its minimum. All right, so then we have to go to the next step, and that is to determine what our allowable shearing stress is. Okay, now this takes a little bit of talking as well. So there isn't just one technique of doing this presented in the book, right? There are a couple of them. So it starts on kind of right below where table 10.4 is. It discusses this problem, and they give one guess that's kind of in the paragraph there. They give one guess that's about 0.45 of the ultimate tensile strength. That value is actually repeated over in table 10.6. It gives you a few different values for different kinds of material for good guesses as far as percentages of your ultimate shearing, of your ultimate normal stress to have your allowable shearing stress, or this is kind of your yielding stress in shear. Okay? And that's what we're going to use, is 0.45. So I put here 0.45 times the ultimate shearing strength. Or excuse me, I keep saying that, the ultimate normal strength. All right. Now, what's the other option? On the previous page, it actually gives a little line right there, and it says some guy named Simonov discusses the problem of allowable stress and shows that the yielding stress for shear is about 0.56 of the ultimate, which is not super far off, but it's a little bit different. And so one of the things I'll tell you is that for problems I give you, I will direct you if it's a problem where I want you to get some correct answer, right? I will direct you as to which of these percentages you should use, all right? Kind of your question, if you're kind of out in the real world and doing this, is just how much more conservative do you want to be? That's kind of the basic question. But in any case, it's always right around half. All right. The next thing we need to do is deal with another material property, and that is the modulus of rigidity. Unfortunately, this is also not something that is just constant. All right, so what we need to do for that is go to table 10.5. And you'll notice here that the way they handle it in table 10.5 is they describe a few different ranges of sizes of the wire, kind of the diameters of the wire, and within a range of diameters, we'll assume that the modulus of rigidity remains relatively constant within that range. I'm not going to ask you to interpolate or anything like that. We'll just use it as within this range. We'll assume that it's some value, but it is slightly variable, and this has to do with the processing techniques that they use to create these really high-strength steels. All right. So for us, what are our range of diameter values here? Okay, looks to me like all of our sizes for this music wire fall within the range that says we're between 0.064 and 0.125 that you might see in table 10.5. Okay, and so I'm looking in that line, and what I want to know is what is my G value? And I'm looking specifically at G in gigapascals. Okay, so that would be 81. All right, and for any of these other sizes, I'll go ahead and say we'll keep in using 81. I don't know. I'll deal with those later, but I'll just make the note right now that this is 81 all the way across the table. All right, so now what? I'll tell you what, I'm going to actually add a line in here and do something a little bit different. I'm going to put a line in here where I calculate my actual mean coil diameter. Okay, I think that'll help me out a little bit with the simplicity of some of my other equations. So for my actual mean coil diameter, what is it going to be? And I guess I probably don't want this in inches. I probably want this in what kind of units? Okay, maybe millimeters. All right. And where should I go to look for this? Okay. I look for the diameter of the rod, which I had up here. All right. That would be right here. And I want to add to this the diametral clearance. Okay. Before I do that, let me lock that in, because I don't want to be moving to other cells there. I want to take that and add the clearance. All right, and then what else? Okay, plus the diameter of the wire. And I won't lock that one in because I plan on being able to copy these formulas to the right. And so I want that to actually update as I copy to the right. Okay, so that's my mean coil diameter. What is C? What is this value right here? You might remember this was called spring index. All right, and that's useful for several things. But we'll go ahead and find this spring index. It's fairly simple. All you do is you take the mean coil diameter, which exists right here, and you're going to divide that by what? wire diameter, right? So that gives us our spring index value. Okay, and just to make a note of this while I'm here talking about the spring index value, it gives us a range through which you can kind of expect your spring index might exist, all right? And it says generally between about 4 and 12. Yeah, we might be a little bit above 12 there. That's not the end of the world, but it's just, those are sort of some guidelines. All right, what's next? Bergstrasser factor. One of our coolest sounding, you know, if you go home and, you know, your parents wonder why they've spent all this money while you're going to school, just tell them you learned about the Bergstrasser factor, and that's going to, you know, really convince them, I think. Maybe not, but, you know, maybe so. All right, so now let's see. We need 4 times the spring index. So 4 times this spring index value. And then we're going to do that plus 2. And in the denominator, we'll do 4 times the spring index value minus 3. Okay, and remember what the Bergstrasser factor does. It accounts for the fact that there's direct shear in the cross-section, and so you need to kind of increase the amount of stress that you predict because of that, as well as there's this other effect that because the wire curves, that creates a stress distribution that's more strong toward the inside of the curve, and you're accounting for that as well with this one factor. All right, so now what? Okay. NA, all right? Why is this the next thing for us to look at? Okay, it's the next thing I have on here, so it's, you know, that's one reason. But there is a reason why I put that as the next thing to put in the table, at least for this problem, where we have this particular set of constraints that have been handed to us. I want you to go over and look real quick at equation 10.9. Equation 10.9 is the spring constant equation. This spring constant equation has K, the spring constant. It has lowercase d, wire diameter. It has modulus of rigidity, G. It has mean coil diameter, D. And it has N, which is the number of active coils. Of those values, which ones don't we know? Okay, the only thing that we don't know in that equation is the number of active coils. Everything else we've now specified for this problem. And so what do we do to find that N? Okay, well, we can rearrange that equation just a little bit. Really, all you got to do is multiply both sides by N and divide both sides by K. All right? And so that ends up giving us a bit of a messy equation. It's one of our messier equations that we're going to have to deal with right here. It is, in its basic essence, a fraction. Okay. The numerator of the fraction will have the wire diameter. Okay. Now, one thing I want to do for this, this is one example of where it's probably going to be helpful for us to return everything to base units. All right, because otherwise it might be difficult for us to chase the units through everything for our sheet. And so I'm going to return everything to base units here. The diameter that I have is in millimeters originally, right? So what do I do to get that into meters? Okay, divide that by 1,000. All right, and then that number is taken to the 4th power. Okay, we're going to take that and multiply it by the G value that we have, right? The G being the modulus of rigidity. I defined that up here, and that's in GPa. So what do I need for that? Okay, so 81, that in gigapascals, that would be multiplying by 10 to the 9th, right? So I take this and multiply by 10 to the 9th. Okay, now in the denominator I have 8 times d cubed, okay? So I have something cubed there. Where do I have D? That's right here. And then what? Okay, divide that by 1,000 as well, because that is in millimeters, the way I have it right now. All right, so then what's my last thing in here? Okay, because I swapped the position of spring constant with the position of N, and I'm trying to calculate N right here, I put spring constant as my last value that I put in here. And that spring constant that I'm looking for is newtons per millimeter. All right? So how many newtons per meter is that? Okay. So I take that, newtons per millimeter. If it takes half a newton to move a millimeter, how many newtons will it take to move a meter? Probably 500, right? So, you know, that's one way of convincing yourself that it's probably correct to multiply by 1,000 here. Okay? So, any disagreements so far? Anyone say, no, it looks like you messed up? Because it's easy to do that while you're working something live like this. All right, this says I come up with 19.3 coils, okay? And I'll just say there's no reason you should be shy about having a fractional number of coils. That's okay to have a fractional number of coils, so don't worry about that. What do I do to find my total number of coils? Okay, table 10.1 in the book, which, you know, that's nice. It tells you right there, look at table 10.1. But we have squared and ground ends. I don't think I made a big deal of that right at the very beginning, but I put that on my original picture, that these are squared and ground ends. For squared and ground ends, you get your total number of coils with the active coils plus 2. All right, the next thing I want to put in here is what is my solid length? Okay, because what we're designing for, one of the things we're designing for is to have a certain amount of factor of safety when the spring is solid, like if you take it all the way down. So that means I need to figure out what those forces are in order to figure out what that factor of safety is. All right, so this solid length is also given in table 10.1. And it just is the wire diameter times the total number of coils. Okay. Well, how do I then go about finding my spring force at solid length? Okay. Right, so this is just our spring constant, or our Hooke's law equation. And to find F, we just take K, which was up here, and multiply by delta. Well, what's delta? Okay, delta is whatever our free length was minus the length at the solid, you know, height. All right, and that gives me 130 newtons or so. F equal K delta right here. It is, well, okay, that's a good question. F max versus this, if I wanted to put a subscript on it, I would actually call it Fs. Okay, maybe I'll put that in, right, because this is the amount of force the spring carries at the point where it goes solid, right? The difference between these two things is that F max is the maximum amount of force we're expecting to see in service, whereas we're not expecting the spring ever to go solid, but if it did, Fs is the amount of force it would be carrying when it was solid. Okay, by go solid, I mean all the coils touch each other and it can't compress anymore. All right. So now, let's look at the shearing stress when it goes solid. For that, we need to go back to equation 10.7. Equation 10.7 says that you're going to multiply by the Bergstrasser factor and multiply that by a fraction. That fraction is 8 times, okay, what we're doing here is doing this at the solid height, so I need to go up here and get the force that exists at that solid height, and then multiply this by the mean coil diameter, right, which I have that up here. Okay, quick question. Do you think I might want to handle this, like how do you think I might want to handle this in terms of units? Okay, you do have some choices, but one way to handle it is with base units. I think that's what I'll do here. So that means whatever comes out of this will probably be in pascals, right? Unless I do some other kind of a multiplication. So I'm going to handle it with base units, which means I'll take my diameter here and do what? Divide by 1,000. All right. And then in the denominator, I have pi times, let's see now, d cubed, okay? And d is the wire diameter. Let me put that in parentheses here. I will also divide this by 1,000, and then that is cubed. All right. Again, I mentioned that's going to come out in pascals if I don't do anything different. What should I do to get this into, if I want to get this into megapascals? Okay. I might want to put a times 10 to the negative 6 in the denominator, right? Okay, so 10 to the negative 6. Okay, question would be, you have a number of pascals. Is that number going to be larger than the number of megapascals or smaller? Right, it'll be larger, so in order to get megapascals, you divide by, oh, I see what you're saying. Yeah, I did it twice, right? I did negative 6 and I put it in the denominator. Thanks for catching it. So if I put it in the denominator, then I would want to do to the 6th. All right, so that should give it to me, unless I have an error somewhere. All right. Did it do it for me correctly there? Okay. All right, so that's my shearing stress when it goes solid. Then what? Okay. Now I'm ready to do a factor of safety at the solid height. Well, how do I do that? Okay. You take the amount that it's okay to have, right, and then divide by the amount that you actually think you're going to have. Okay. So that gives us this value for my allowable shearing stress divided by the shear stress that I actually have when I go solid. And what that tells me is that for this spring, if I take it to where it's solid, then I will yield the material. All right? Why do I know that? Or I expect that I will yield the material anyway. Because the number there is less than 1. Okay, so another thing that it tells us we should be looking for in here is something that's called a fractional overrun to closure. That's a kind of a mouthful. What I want to do for that is go ahead and find that expression here in the book. Okay, the weird thing about the fractional overrun to closure is that it doesn't give it to you in terms of that number. You have to kind of rearrange this equation 1017 in order to get that number. Okay, which if you do that, kind of the starting point is to take the fraction of the force at the solid height, right, which I had that up here, spring force at solid height, divided by the maximum force that we expect for it to have to carry. And what was that? Okay, 104.75. And then what? Okay, then we'd subtract 1 because that's what's in the parentheses there. And this tells me that my fractional overrun to closure is 0.24858. What's my guideline for that number? Okay, it says in the book, it's a good idea to try to make sure this number stays larger than 0.15. So in terms of that number, we're okay. The big problem with this particular spring that we have designed right now is that it actually will yield, and that's not something that we want. All right, I have these on here as well, just so that they're kind of a matter of interest. These aren't necessarily part of the design question, but what would my maximum shear stress be in actual just normal operation? All right, well, it works kind of very similar to what it would be at the solid height. As a matter of fact, let me do this. Springs force at solid, it's easy enough to put it in there, I guess. Sorry, this is the one I wanted to look for. All right, so I can put this in right here, I think. What do I change? Let's see now. I want to get all of this stuff and do what with it? Put it right here. What do I change? Okay. Right, so instead of the spring force at the solid height, I need to put this D23 and instead change it to the amount of force that I have at my maximum during my normal operating, right? So I'm going to put in this value, and then I probably want to lock that in. Okay? And then if you're curious what that factor of safety would be, the calculation is very similar. You just take the amount of stress that you think will cause failure and divide by the stress you're actually experiencing. So even that, it would even yield just under the maximum amount of force, even if you didn't want to make it what's called solid safe. Solid safe springs are ones that will not yield even if you take them all the way solid. Which one? The last one? This one? It's just the amount of stress that causes failure, which would be the 913.4 divided by the amount of stress it's actually experiencing, which is the 1123.49. That makes sense? That's, for our factors of safety, that's the typical definition, unless we have a really fancy equation that gives it to us for our particular context. All right. So we've done all of that. What do you think next? Okay. And this is where I find out if I did any relative references where I wanted to have an absolute reference. I a lot of times miss some. But I'll try it out and see if this works. All right. So let's check this out and see if I made an error somewhere. This is a little bit tricky to do live. So let's see. NA. All right. It doesn't surprise me that that would be where I might have an issue. What do I have here? All right, my D7. All right, that needed to be an absolute reference. So I'll fix that. Anything else? Was that it? Okay. I think modulus rigidity is fine. Oh, yeah, I got you. In that table, it put in a different value as I drug it across, right? It put in an... right. Let's see now. Gotcha. C7. All right, and I think that fixed that. And someone was mentioning the modulus of rigidity. The fact that that was just 81 right there, it made it want to kind of go along and increase it by 1 each time. I want to make that 81, like that. All right, so let's check out some of our numbers. Did we help ourselves a little bit with our factor of safety against being solid safe? Okay, a little bit, but not quite enough yet. All right, so let's drag this the rest of the way across, and we will have to go back up and fix these again. Okay, I left this as a row of values here for G. Why do you think I did that? Because it can change, right, based on your wire diameter. It doesn't for this problem, but it can change if you go outside one of the ranges that we had for that modulus of rigidity. All right, based on what we see here, what do you think we should recommend as far as a spring is concerned? Okay. This gauge right here looks to be like it's pretty good. Are there any problems, with that gauge? Okay. This right here, you might not really like that very much. Why not? Yeah, so the book says, if you can, try to make that value about 0.15 or higher. If you read the surrounding text around that, the basic reason why is that springs start becoming nonlinear when you are at the, before you even start applying force to them, right at the very beginning of their deflection, they tend to not be super linear at that point, and they also tend to get less and less linear if you get them very close to being solid. And what they're trying to do there is say, you should give yourself a little bit of slack, a little bit of buffer room for your overrun to closure. So this is a little bit tight. What that actually means in terms of physically what the spring is doing, it means the coils are super close together when you have the spring, at that location. So, that there's a lot of reasons why that might not be good, because it doesn't give you a whole lot of space. That if you were wrong in what you were expecting, then it doesn't give you a lot of space. Okay. Well, what do you think we can do about that? Can we go any larger? We can't go larger. We can't go smaller because why? Factor of safety is less than 1. Let me suggest something. We can go back to the drawing board with our original problem, and we can think, why did I have this 30 centimeters of original height? Okay, so this is a bigger question for whatever this, if this is part of a machine or something, it's a question for, was there a real reason I had to have that limited to 30 centimeters? If I don't have to have that limited to 30 centimeters, does that help us out at all? Okay, let's try maybe 35 centimeters. Okay, and what you see there is it did, having it 35 centimeters long changed it a little bit in terms of our shearing stress at the solid height, but what else did it do? Okay, we now have this column over here where we've increased the wire size by 1 gauge, right? And now we're good in terms of our solid safety. And what do we see now in terms of our fractional overrun to closure? You're closer. And I would actually at that point start thinking, yeah, maybe close enough. All right, since those are kind of guidelines anyway. You could continue this a little more. You could take it to 360 or something like that. And kind of tweak it a little bit until you felt like you were in good shape. All right. I want you to have a physical idea of what the meaning is. One of the things that this, tells you here is how many total coils you have. Look what happens with this number, right? The way that you are, as you increase your wire diameter, you're keeping your coil diameter the same. So to keep the same spring constant, what are you doing? You're increasing the number of coils. right? So as you increase that number of coils, now your solid height gets higher and higher because you're increasing your number of coils. And that's ultimately what's making it to where the, it's more solid safe, is that, you're increasing those number of coils, and now it will basically go solid at a higher height, and so before it ends up yielding the spring material. All right, so anyway, you kind of get the idea. This is what I've done here is a tabular solution to a discrete design problem, and hopefully that helps you with the idea of how you might construct a table when you're doing a design problem. Yeah?
We said that as we increase the wire diameter of our spring, it increases the number of coils that we have.
So the reason you have to do that is that increasing the wire diameter would, if you didn't do anything else different, it would make your spring stiffer. Okay? So if you want to back that back off and get back to the same spring constant you had before, you can increase the number of coils, and that basically would be similar to if you're twisting a rod. The rod will twist more and more the longer it gets, right? So that's essentially what you're doing in the spring, is you're giving it more material to twist, and it makes it a softer spring. All right, any other questions? All right, well, I will see you guys next time.